Okay, so I'm just going to continue on from two of the previous videos showing the setup of the function generator here at the bottom and the oscilloscope here on top, and we're going to just connect them to each other and so we can monitor using the oscilloscope the waveform that is coming from the oscilloscope, or sorry, coming from the function generator. So we're going to use two oscilloscope leads. We have a lead going in to our oscilloscope, and then we have a lead coming out from the main 50 ohm output on our function generator, and the other end of those leads are simply crocodile clips. So we simply match the black crocodile clip as the ground to connect them together, and then the signal crocodile clip, the red one, they're going to connect together in this case. Just simply monitor the output of the function generator. So I'm going to connect it up first of all and set a frequency on the function generator of 1 kilohertz to start off with, and we'll look at what that looks like on the oscilloscope, and we'll look at how we would go about measuring that. So I'll set it up here using the dial down here to 1000 hertz. 1 kilohertz. So there is about 1000. Oh, that's not too bad there. So we're in 1.004 kilohertz. You'll see there we're on the 3 kilohertz range, so that's good to let us get our 1 kilohertz signal. And we're just simply on 10 volts peak to peak. So if we go up and look now on our trace on the oscilloscope, you'll see we have some of the trace there. We don't have it all. What we can do is we can hit the auto set button in order to achieve a better trace, or we can try and adjust the oscilloscope ourselves to get the trace into some sort of form that we can read. First of all, just check our channel 1 that we're on. We'll just check our settings. We're on AC coupling, as it's an AC signal or sine wave that we're working with. We want to make sure we're on probe times 1, two important ones for us at the minute. So just simply by adjusting the scale here, dial on the right hand side here, we can get the waveform into some sort of format that we can observe. So I'm just turning it to the left slowly, and you can see the sine wave coming much clearer into the picture. So that allows us to be able to analyze it, to measure it. Although we do have some self-measuring from the oscilloscope itself. For example, here we have peak-to-peak voltage here on the left for channel 1, and we have our frequency down here at the right-hand side. It may not be a case that you're always using an oscilloscope that allows you to see that or does the measurements for you, so it's good to be able to understand how to measure these yourself. So in terms of the frequency, in order to measure the frequency, we want to look at the periodic time. So that's the length of time it takes for one cycle of the waveform. So you'll see from here to here is one cycle of the waveform. We have one positive cycle, one negative cycle to complete one full cycle. You'll see that the full cycle of the waveform covers 2 squares or 2 divisions, and you'll see that our time-based setting here is 500 microseconds per division, so that would give us a total of 1000 microseconds for the length of time it takes for one cycle of that particular waveform. So from that we can calculate the frequency. So as I say, we have 1000 microseconds for our periodic time. So our periodic time is simply our frequency is simply 1 over periodic time. So in this case it would be 1 over 1000 microseconds, so 1000 by 10 to the minus 6, and that will give us 1 kilohertz. You can see there on the screen we have roughly about 1 kilohertz there shown. In terms of measuring our voltage, you'll see that we're on, or our amplitude, we're on 2 volts per division. Now we're getting a peak-to-peak reading here of 10.2, 10.4, slightly different from the reading that we're getting on the dial here on the on the function generator. I would tend to go by what the oscilloscope is reading and take that as your more accurate reading. But we can take a reading ourselves simply by judging in terms of the number of divisions and the number of squares. So we have, in this case, if we want to look at our peak to peak voltage, we're on 2 volts per division. So our waveform is covering 1, 2, 3, 4 full divisions and roughly 2 half divisions, which will give us our 10 volts. So basically 1 volt for each half division and then 2 volts for each division that the waveform spreads across. Now you can also use the position adjustment here if you want to adjust up to the edge to get the waveform on the edge of a division, if you feel it makes it easier to read. And you'll see there the waveform just a fraction above, fraction greater than the 5 squares, the 5 divisions there. So you can do that as well. You can also do that on the horizontal as well, as far as reading your time base is concerned, using the position here as well. If you want to line up, you can see the waveform moving left and right as I adjust the position on the time base. So you can line that up as well with the divisions on the oscilloscope to get a better way to judge the value of the waveform. So what I want to do now is just look at a different value for a sine wave. We're going to increase the frequency to 10 kilohertz, from 1 kilohertz to 10 kilohertz. So we look at a function generator, we're on the 3 kilohertz setting, so we're not going to be able to get 10 kilohertz on that setting. So we're going to have to jump up here to the 30 kilohertz setting. So I'll just press that in, and you'll see the oscilloscope picture has changed. And then we just want to make some fine adjustment here to our adjuster here to get this closer to 10 kilohertz. So there we're roughly there, 10.03 kilohertz. So if you see there the screen, because the frequency has increased, so there's more repetitions of the waveform per second, and we haven't adjusted anything on our oscilloscope. Our waveform sort of concertinaed and squeezed in on the screen, and as it's sitting like that there, although we do have the different measurements shown there, you can see the 10 kilohertz has come up here. We're still on the same 500 microseconds per division. So you can see where we had basically half the previous waveform in 500 microseconds. We have 1, 2, 3, 4, 5, about 5 repetitions of the waveform in 500 microseconds this time. So it's a much greater frequency than the 1 kilohertz. So what we want to do is, the way that the screen's currently set up, it's not very good for us to be able to read the oscilloscope. So we're going to use our scale adjuster here at the side, and we're going to turn it to the right in order to stretch out the waveform. And what we're doing is we're decreasing the time per division in order to be able to look at to monitor the waveform. So we'll take another one. So there we're now on 50 microseconds per division, and you'll see now our waveform. We have the waveform as it was before, the same sort of view where it covers 2 squares, so 2 divisions, but at this time each division is only valued at 50 microseconds per division. So our periodic time for this 10 kilohertz waveform will be 100 microseconds. So we can calculate the frequency again. From that we can calculate our frequency. F will equal 1 over 100 times 10 to the minus 6, which is 10 microseconds in this, 100 microseconds in this case, and that will give us 10 kilohertz as we have here shown on the oscilloscope. Just one more thing I just want to show you regarding the waveforms, and that is just to take a look at a square wave and what it looks like on the scope. Although we've looked at it before on the oscilloscope's own sort of calibration square wave, but you can see there we can change the square wave, change the wave to a square wave, and we have a peak to peak value for our square wave here. and you can see the values more or less remain the same and the frequency remains the same, just the shape of the waveform changes. So I would suggest that you would sort of, as a first step, would be to connect the scope and the function generator together, and to just practice setting the function generator up to different frequencies and different voltage values, and then measuring them on the oscilloscope. So getting familiar with the different scale adjustments, position adjustments, and of course our different settings here on the side.